Hello there! As promised in my last video, I am back with a new one at the end of September. In these 3 months of hiatus, I became interested in the topic of AI voice cloning, indeed to clone my voice, but with no Italian accent. So that you can assess the pros and cons of my clone, I'm gonna switch to it for the remainder of the video. In 3, 2, 1...
Now, this is the tutorial I followed from SECourses. It's the best I could find, but can still be improved in precision, clarity, and length. Therefore, here is that tutorial revised by me. Firstly, we must fulfill 4 prerequisites. Download Visual Studio 2022, and in its installer, just select Python development and its native development tools. Next, download Git for Windows and install it. The defaults are fine except for the editor, which you can choose freely. Then, download Miniconda with Python 3.10 and install it. Again, the defaults are fine, but you might want to also clear the package cache, and perhaps even move the installation folder from a smaller solid-state disk to a bigger hard disk, like I did. Finally, sign up to Hugging Face, search for segmentation, fill in all the fields, accept the conditions, and go to Settings, Access Tokens. Here, create a new write token for Ozen Toolkit. Secondly, we must clone 3 repositories and amend them slightly. So, run the Anaconda prompt and change directory to Miniconda 3 or wherever you prefer. Then, type git clone, followed by these links to their respective repos. Now open the Ozen Toolkit folder. Click on requirements.txt and specify the transformers version like this. Open ozen.python with Notepad. Click on Edit and replace Whisper Large V2 with the right model according to the VRAM of your graphics card. Since my 3070 only has 8 GB of VRAM, I have to use the medium one. If you've changed the default Conda path like me, create a new text document called Custom Conda Path and enter it. Now also copy and paste this file into the DLAS school folder. Finally, open the TorToiSe TTS fast folder, TorToiSe, and inference.python with Notepad. Here, replace the stock split text section with this one, which you will find in the video description. Thirdly, we must set up the 3 tools correctly, which is not entirely trivial. To begin, run the Anaconda prompt and type this string to update Conda to its latest version. Next, go to the Ozen folder, click on Setup Ozen.bat, and patiently wait for the very slow process to complete. When done, type Conda, activate Oza in the prompt and copy-paste the command in description to install the proper version of PyTorch. Then, go to the DLAS School folder. Click on Setup DLAS.bat, and again wait for the procedure to finish. When done, in the prompt type Conda activate DLAS, followed by that same command as before. Now, to replace transformers with its correct version, copy-paste these other two commands. Sadly, there is no automatic setup for TorToiSe, so we have to do this. Manually create its virtual environment, activate it, and employ the PyTorch command for a third time. Finally, change directory to TorToiSe TTS fast and enter the strings to properly set it up, including a specific version of transformers. If you have followed my instructions to the letter, everything is ready and set to actually initiate the cloning sequence at last. The first phase consists of speech-to-text transcription and is handled by Ozen Toolkit. This takes a long recording of your voice, segments it into small parts and transcribes them into 2 text files, training and validation. You just have to drag and drop your audio file over here and copy-paste the Hugging Face token when prompted. When it's done, you will find a folder within Output that contains the audio segments and text files. Now you need to open them to correct possible transcription errors and verify that their encoding is UTF-8. If it were not, click on File, Save As, change the encoding, save, and replace. a footnote on the unabridged voice. The longer and the higher the quality, the better. For reference, I used DaVinci Resolve to fuse together almost an hour of audio clips from 14 of my videos, which Ozen then split into a dataset of 234 samples, 186 for training and 48 for validation. The second phase is the actual training of a deep neural network, thanks to the DLAS framework and its tools. In a nutshell, an AI slowly but steadily learns to speak with your voice, just like a kid in real life. So, how to properly configure the training session? Click on Start DLAS to open this cool user interface, which allows you to easily change all the relevant settings -1. Let's explore them, shall we? Project name. Choose whatever you want. GPU ID. If you own multiple graphics cards, select the one you wish to use. Enable gradient checkpointing. Keep this enabled to save model checkpoints during training, i.e. to freeze consecutive learning stages. Moreover, it also greatly reduces VRAM usage. Half precision floating point. According to the repo author, it slows down performance instead of speeding it up, so leave is disabled. Weights and biases and tensor board loggers. Pick one, both or none. Dataset path. As the name suggests, select a path to the folder created by Ozen that contains the audio samples and their transcripts. Train and validation batch sizes. Ideally, you should set the respective number of samples defined by Ozen. In my case, indeed 186 and 48. However, with 186 as the train batch size, my 3070 ran out of memory, so I had to cut that value in half. Why half, you say? In order for you to understand, I need to explain the meaning of step, epoch, and steps per epoch, with an example. Suppose my dataset consists of 15 samples, 12 for training and 3 for validation, and I choose 6 as the train batch size. As soon as the model processes 6 training samples, it achieves its first learning step. So a step is a pass through the train batch. Once the model processes the other 6 samples, not only does it finalize its second step, but also its first epoch. So, an epoch is a complete pass through the entire training sample set. Bearing these definitions in mind, it becomes clear that the number of steps required to reach an epoch is 2, in this instance. If instead I had picked 4 as the train batch size, steps per epoch would have been 3, or 4 if I had chosen 3, and so on. You get the idea. Okay, but how do you decide whether and by how much to equally divide the training sample? It all depends on the amount of VRAM available on your graphics card, so all you can do is try. That said, let's now move on to the number of steps. Considering that my 3070 with 184 tensor cores reaches 280 steps in almost 15 hours, it's obvious that 50,000 steps are far too many, regardless of how many tensor cores your VGA has. Here I suggest doing a quick test with just 10 steps to see how long it takes, and then make a decision on this basis. Anyway, a reasonable number could be between 200 and 2000. Warm-up steps is self-explanatory. Leave it as it is to include one warm-up step before training. Gradient accumulation step is, simply put, a truly helpful memory-saving technique. If set to 1, the model computes gradients and updates its parameters every step, which leads to higher VRAM usage. But it's set to 4. So the model sums the gradients of each step but only updates its parameters every 4th, resulting in lower VRAM usage. Only increase it to 8 if you keep getting out of memory errors. Learning rate or speed is self-explanatory, but I haven't experimented with it since the default value seems good enough. Learning rate stepping represents the 4 steps numbers at which the learning rate is halved. According to the author, if your dataset contains less than 500 samples like mine, The first number must be your steps per epoch times 10, applying the same logic. The second number is S by E times 20. The third is S by E times 28. And the fourth is S by E times 36. As a result, since my steps per epoch are 2, I have to set 20, 40, 56, and 72. On the other hand, if your dataset consists of more than 500 samples, you can keep the 4 predefined values. Save EMA model and the states serve to resume an incomplete training session. But I tried that, and it didn't work, so leave them both unchecked. Training seed. If reproducibility rather than randomness is desired, always set the same number. Print status, save checkpoint, and visual debug are frequencies expressed in terms of steps, which can be set at will, perhaps 5, 10, and 10. If so, the model parameters are displayed on screen every 5 steps, while its checkpoints and debug images are saved every 10. The latter, I honestly don't know where. I'm sorry. Now, if your card has less than 24 gigabytes of RAM like mine, click on Advanced Settings and reduce the training workers from 8 to 1. This really helps to prevent potential slowdowns, freezes, and out-of-memory errors. The last setting to be changed is strangely absent from this user interface, but it's fundamental: the validation frequency. You can find it here: codes, utils, basegpt.yaml. Scroll down to val_freeq and set it equal to your saved checkpoint frequency. Finally, click on Start Training and maybe go to sleep to travel through time and thus skip the long wait. In the end, you'll find all the saved checkpoints in experiments, project name, models. But which is the best one? Open the log and scroll down. Theoretically, it should be the one with the lowest text, MEL, and GPT losses. If you wish to see them in graph form, go back to the main folder, click on Start Training Monitor, and copy-paste the link into your browser. The third phase is the long-awaited text-to-speech synthesis, powered by TorToiSe Fast. Hence, open the Miniconda prompt. Type conda activate /TorToiSe and change directory to the script folder inside the TorToiSe TTS Fast 1. Then, type Python TorToiSe _TTS.py --help to display all the possible options. Yes. They are quite overwhelming, but don't worry, I'm going to explain the most relevant ones for our purposes. There are 6 presets, each with an increasing number of autoregressive samples and diffusion iterations, resulting in higher quality. In fact, the more samples and iterations that are set, the greater the chance of creating a compelling voice and refining it, respectively. Of course, the more there are, the greater is also the cost in computing time, so choose them wisely. Voice Fixer should be set to false, since it's pretty bad. The output directory can be selected at will. The output candidates should not be more than 3 to avoid increasing the processing time too much. Moreover, the first one is usually the best. As I stated before, use the same seed if you want reproducibility. Text split refers to that section of code we edited in the inference file, and it's indeed used to separate each phrase with a /. There are 3 voice encoders available. UniveNet is the original. Big Vegan Base is way better, and Big Vegan is even better. As for the autoregressive checkpoint, copy-paste the path of the one selected in the previous phase. Temperature controls the output accuracy. A value closer to 0 produces a more similar voice, while a value closer to 1 a more varied one. The penalties for the output length and repetitions can vary between 1 and 8, i.e., between more and less length and repetitions. Top P controls the output monotony. 0 is more boring and 1 is less boring. Maximum mal tokens also limits the output length, so it should be set to its max value of 600. Conditioning-free diffusion should always be switched on because it greatly enhances realism, which can be adjusted via a knob. Its values range from 0, more natural, to 4, more artificial. Diffusion temperature is somewhat similar to Top P, in that it controls the output vividness. 0 is less lively, and 1 is more lively. Low VRAM, half precision, and no cache are self-explanatory, and should only be changed to true if you are really running out of memory. One at a time, and in this exact order. There are 3 samplers at your disposal, P, DDIM, and DPM plus 2M. In theory, this would be a ranking from worst to best, but I don't know why in practice the latter gives me poor results, so I use DDIM. Now that you have a clearer picture of the main settings, open a text editor to prepare the final command for use. Type Python TorToiSe_TTS.py as before, then add the options you want with a space in between. Lastly, append the text in quotes at the end, with each sentence separated by a /. A tip for best results: each sentence should be no longer than 140 characters, including spaces. After copy-pasting it into the prompt, TorToiSe will convert such text into an audio file in which you can hear your own replica speaking. Talent is a factor, but training and focus are what truly define someone's success. Anger and frustration are quick to give power, but they also unbalance you. The 4th phase is entirely optional, but recommended to further improve the audio quality. Use Enhanced Speech, a free tool from Adobe. How to use it should be clear to everyone, or so I hope. Talent is a factor, but training and focus are what truly define someone's success. Anger and frustration are quick to give power, but they also unbalance you. Talent is a factor, but training and focus are what truly define someone's success. Anger and frustration are quick to give power, but they also unbalance you. I also hope you have appreciated my efforts to explain as much as I can and to the best of my skills, which are quite limited in this field. Admittedly, I am not an AI expert, but just a guy who wanted to clone his own voice and share with you what he learned along the way. If you did appreciate them, please like, share, and subscribe. As always, many thanks for tuning in, and fare you well for now.